Okay, so good morning again. So today we have Jorge Lillo from the Astrobiology Center, and then to introduce Jorge. So Jorge did his undergrad and master's studies in physics and astrophysics at the Universidad de La Laguna in the Canary Islands. He carried out his PhD at the Astrobiology Center, where he studied planetary systems exploiting data from the Kepler mission and from the Calar Alto Observatory. In 2015, he moved to Chile, where he worked at the European Southern Observatory as an ESO fellow. And then now, back in 2019, then he returned to the Astrobiology Center, where he started a postdoctoral research position, first funded by the Maria de Maeztu of the Astrobiology Center. And right now, I think he was awarded a Junior Leader Fellowship funded by La Caixa Foundation. Is that correct? Okay, so and today he's going to talk about 3 special multi-planetary systems. So Jorge, whenever you're ready, please go ahead.
Okay, I hope you can hear me well. Cool. So thanks, Izaskun, for the great introduction and for co-organizing these seminars. I am Jorge Lillo. I am a Junior Leader Marie Curie Fellow at the Center for Astrobiology, and today I would like to bring to your attention an important part of the exoplanet exploration. Besides the detection of thousands of extrasolar planets, I would like to highlight here the importance to foster programs devoted to the in-depth characterization of some planetary systems, and more specifically in an astrobiological context. So the Maria de Maeztu Seal of Excellence of the Center for Astrobiology is based on the development of 4 specific scientific and technological priorities. These are the in situ exploration of solar system bodies, the identification of key biomarkers, the lab simulations of extraterrestrial environments, and the study of extrasolar planets. This talk is mainly framed in the last item in this list, but I will also provide some insights into the second one. After detecting our favorite extrasolar planet, the main question we may wonder is, how does it look like? Which of these, among these landscapes that I'm showing here, could we expect in such far away world? Of course, these images correspond to real bodies in our solar system that you can easily identify here. However, unfortunately, we cannot perform this type of amazing landings on the surface of our favorite extrasolar planet. In the vast majority of the cases, the only get from our favorite planet is actually this one. And no, your screen is not broken here. It is simply that most extrasolar planets are so far away that we cannot visit them or obtain direct images of their surfaces. Only in a couple dozen cases, we managed to directly see some planets using adaptive optics techniques, like in these 2 examples here that I am showing. On the left, we have HR 8799, and on the right, we have Beta Victoris B planet. Instead, for the large majority of the cases, we will need to rely on indirect techniques where we see the consequences of the presence of a planet in the stellar observables. One of the most successful techniques is the transit method, where we see the flux coming from a star, dimming periodically because of the presence of a planet. This planet passes in front of its host star, as seen from Earth, and blocks part of its light. The larger the planet, the deeper the transit will be. And hence we can infer the size of the planet by detecting these dimmings. The other relevant technique is the radial velocity, where we see the reflex motion of the parent star as it moves around the center of masses of the system due to the presence of the planet. This is translated into periodic Keplerian changes in the radial component of its velocity that are measured through the Doppler effect. By using this technique, we can measure the planet-to-star mass ratio. So if you think about it, having information from both techniques, transits and radial velocity, allows us to obtain a bulk density of the planet. And at the end of the day, this already gives us the first glimpse on its composition, allowing us to discern between gas-dominated planets like Jupiter and rocky worlds. If we additionally have a very good precision in the mass and the radius, and we know the chemical abundances available in the formation of the planet, we can also infer a first approximation to its internal structure, distinguishing the mass fraction located in the core, in the mantle, and in the atmosphere. But getting high precision masses and radii is critical not only to break the degeneracy of the planet interior models, but also to allow atmospheric studies, perform comparative exoplanetology by exploring the properties of planets at different stellar irradiations, but form within the same environment, and to understand planet populations and unveil trends or gaps in the different parameter spaces that inform us about the formation and evolution processes. During the past 30 years, we have focused on detecting a myriad of extrasolar planets with a plethora of properties. The current space and ground-based capabilities now allow us to go beyond the exploration and enter into the depth characterization of these systems. But intensive campaigns with tens or hundreds of spectra are needed to really go down to 20% precision in density. Here I show now the mass radius diagram of known small planets with the mass in the x-axis in Earth masses, and in the y-axis I am showing the radius in Earth's axis. I am only showing here planets smaller than 4 times the Earth radius and less massive than 50 Earth masses. However, so you see a lot of points here, but if we focus only on those planets with densities known to better than 20% precision, we get this other diagram with much less points in it. But still, we can start distinguishing some populations here. A population of rocky, Earth-like density planets, and a population of less dense planets, thus still retaining a large fraction of their atmospheres that we call mini-Neptunes. In this talk, I will present the results we obtained last year on 3 multiplanetary systems that are populating this region. These systems are neither the good, the bad, nor the ugly, but the compact, the young, and the habitable. And they are K232, K2233, and LHS 1140. So let's start by the first one, by the compact one, K232, which I will show it is a scaled down version of our solar system. K232 is an early K-dwarf star, slightly smaller than our own sun. The K2 space mission observed this star during its campaign number 2 along 80 days, and Silkov and collaborators in 2016 detected 3 planets in this system. Planet B, here, at 9 days orbital period, planet C at 10 days orbital period, and planet D at 31 days orbital period. On the same year, using HARPS and PFS data, Dye and collaborators confirmed the planetary mass of planet B and provided upper limits to the mass of the 2 external planets. In 2017, Pettigura and collaborators used high-res data from Keck to further constrain the masses of the planets, decreasing the mass of planet B, the precision on the mass of planet B by 25%, and constraining the external planet mass to around 11 Earth masses, although still with large uncertainties, as you can see, for example, in this case. Interestingly, in 2019, Heller and collaborators found a very small internal planet in the system with a periodicity of 4.3 days that wasn't detected in the discovery paper of this system. In April 2017, we started a follow-up campaign with HARPS at La Silla Observatory in Chile, within the context of a large program to obtain precise mass measurements of planets in the edge between rocky and gaseous compositions. We obtained 200 measurements within 1.5 years. We combined this with the existing data set and performed an homogeneous reduction and radial velocity extraction of all 242 HARPS measurements, including those published in Dying et al. And the new ones. This plot here shows the entire data set together with the radial velocity model. And the individual radial velocity curves are shown in these panels here, one per planet. And you can see that they are clearly detected in our data. We combine these radial velocities with an independent extraction of the K2 light curves, so the transit technique, to perform a joint analysis of the radial velocity and the transits. Here you can see the full K2 light curve and the individual transits of the 4 planets with the different colors. And here in these panels, you see the phase-folded transits for each of the 4 planets. As a result, we could measure the masses of the 4 planets in the system for the first time, and hence provide their bulk compositions. We found the inner small planet to be 2.1 times more massive than the Earth, thus confirming its rocky composition. It was the first time we could measure the mass of this planet. We found also that K232b is a Neptune mass planet, slightly more inflated. And we found the 2 external planets to be very similar in mass and radius, having 8 and 6.7 Earth masses respectively. Our data provides for the first time reliable masses for all planets in the system and allow us to think about their composition. Looking at the system in this scheme, a first thought that came rapidly to my mind was that the architecture of this system resembles very much that of our own solar system. With a rocky planet in the internal parts of the system and 2 external Neptune-like planets separated from the rocky world by a gaseous giant. And all this in a compact configuration with all 4 planets within 10% of the Sun-Earth distance. So K232 is truly a compact scaled-down version of the solar system. The inner rocky planet and the gaseous giant here, these 2, indeed straddle the so-called mass period or evaporation valley. The underlying cause of this structure, of this valley, still remains uncertain, so finding planets at both sides of the valley and within the same system is key to illuminate the formation and evolution processes that sculpt this gap. If we now focus on this new panel, which I am showing the mass radius diagram and the planets in the system, the properties of the planets in this system that were known before our own work. And here is how the system looks right now, showing that we could place the 4 planets with reasonable uncertainties in this diagram and showing the wide diversity of properties that this system contains, from rocky, Earth-like planets through Neptune-like worlds to sub-Saturn gaseous giants. Although still very uncertain, we performed an internal structure of the inner rocky component, K232e. We found that its mass and radius is fairly well explained by a large core mass fraction. It is thus likely that the planet has a scarce gas envelope and mantle, hence having a Mercury-like structure in a size larger than our own Earth. This is indeed a similar result than the one for K2229, which we published in 8, and becomes another example of a potentially large core planet with a scarce mantle. The origin of this depletion in the mantle mass ratio might be telling us a lot about the history and formation of the planetary system, and maybe about our own solar system. Unfortunately, the uncertainties are still quite large, mainly due to the poor constraint on the planet mass. So reducing the core mass fraction errors by a factor of 2 would require a mass determination with a 10% precision. This would require thousands of HARPS measurements, and we estimate more than 400 ESPRESSO measurements, both of which seem very challenging for a single planet. So K232 is just a compact scaled down version of the solar system. We determined the masses of the 4 transiting planets through an extensive radial velocity monitoring campaign with HARPS. It contains planets at both sides of the evaporation valley, with the inner planet potentially being a large Mercury along an analog, having most of its mass residing in its core. Time now for the jump. This system is K233. K233 is a slightly cooler star than K232, than the previous one, and most interestingly, it has a determined age between 150 and 750 million years, so it is very young. 3 planets were detected and validated by David and collaborators in 2018, with 2 Earth-sized planets in interior orbits at 2.5 and 7 days, and a 3rd planet with 2.4 Earth radii and an orbital period of 24 days. But no mass measurements were provided for these 3 planets. They were only validated through statistical techniques and the transit method. And this is probably because of this scary light curve here that anyone's working on radial velocity would be scared of, because they show large photometric variations, typical of such young stars. We reconstructed the light curve following the same principles that I explained before for K232, and we could detect, again, we could redetect, let's say, the transits of the 3 planets with a fairly high precision here. Here you see the full light curve, and here you see the individual transits of the 3 planets. And when I say this is scary, because then we followed up the star in an intensive campaign with more than 120 HARPS measurements along 100 days with a strategy of 2 to 3 data points per night and a relatively high cadence to properly sample the variations due to the stellar activity. Stellar activity contaminates our radial velocities because they produce some radial velocity variations that are mixed with the Keplerian signals from the planets. But thanks to this, to our techniques, we clearly detect the rotation period. Here in the periodogram is this large peak here. And when removing this activity signal from the radial velocities using Gaussian processes, all 3 planets clearly pop up, as you can see this here: planet B, planet C, and planet D, above the significance level. So we performed a joint analysis of the light curve and radial velocity data set, again, by using our own techniques. And here I'm using the phase-folded radial velocity curves for each of the 3 planets after removing the median Gaussian process noise that takes into account the stellar activity. And you can see the clear detection of the 3 planets. As a result, we could measure for the first time the masses of the 3 planets in the system. We derived a mass of 3.3 masses for the interior planet, 5.1 Earth masses for the 2nd planet, and 8.3 Earth masses for the external planet in K233. Given the radii and masses, we can conclude that the 2 inner planets are actually rocky worlds suffering a relatively high stellar irradiation, while the outer planet is probably a mini Neptune at a much longer period. When placing the planets in the mass radius diagram, we see how they clearly lie at both sides of the radius valley, with K233b more compatible with an Earth-like composition, while planet C seems to be slightly denser. We performed a similar internal structure than the one I explained for K232e, and indeed we obtained a core mass fraction of about 45% for planet B, which is compatible with the core mass fraction of the Earth, and a very large core mass fraction on the other side of 94% for planet C here, in the same line as in the previous case of K232e, which means this is probably another case of a Mercury analog. However, the still large uncertainties in these two small planets prevent a definitive answer to their bulk internal structure. If we now zoom out in this mass radius diagram and we only include planets around young stars, meaning stars with ages below 1 gigayear, we really find out how unique K232, the K233 planetary system is, with the lowest mass planets confirmed around a young star, and most importantly, the first rocky worlds in such an infant system. This outstanding case thus provides the key information about the early stages after the formation of a multi-planetary system, including the first empirical timescales for planet migration of such small worlds. In this diagram, I am now showing the age of the star in the y-axis and the orbital distance in the x-axis for all these young planetary systems. The color code indicates the number of planets in the system. And interestingly, we are populating this regime, this young regime, quite efficiently, and we already know several tens of young planets. But K233 stands as one of the few systems with 3 or more planets known at this age. Its architecture also resembles that of Kepler 411 with a similar spectral type but a slightly younger age. To summarize this system, we monitor the radial velocity of K233 multiplanetary system with HARPS in an intensive campaign over 100 days. K233 is a young system with an estimated age between the Pleiades and the Hyades, and one of the few at these infant ages to host 3 or more planets. Indeed, the planets reside at both sides of the radius gap, and the 2 inner components become the first rocky worlds around a young star. The internal composition study is still poor, but points to an Earth-like structure for planet B and a Mercury-like composition for planet C. And we finish with the habitable component of our trio. LHS 1140 is a habitable world next door. So LHS 1140 is a mid-M dwarf. This means that the star is around 20% in mass and radius that of the values of the sun, and it is located at a distance of around 10 parsecs. In 2017, Dittman and collaborators found a super-Earth around this star in a 24-day orbit. They used HARPS and M-Earth data to estimate its mass and radius. As you can see here, determining the mass with a precision of 27%. Additional HARPS and M-Earth measurements, together with an Spitzer follow-up observation that you can see here, led to 2 years later to the confirmation of an additional inner planet in the system with a smaller radius and 3.8 days. Indeed, if you focus on the Spitzer observations, you can see a double transit of both planets consecutively. So first planet B and then planet C. So far, the precision on the mass of these planets was 13% for planet B and 22% for planet C. Interestingly, planet B is inside the habitable zone of this star, which makes the system very interesting. But we already knew the planets in this system, so why revisiting the system again? First, at the time we proposed the observations, we knew the TESS space mission was going to observe this star, and so it would be able to improve the radius determination. Also, the mass values were not excessively precise for the great interest of this system, so an improvement in the mass was also necessary to start analyzing the internal structure of the planets. We also wanted to explore the possibility of co-orbital worlds in the context of the Troy project. So these are planets sharing the same orbital path, especially in the case of the habitable zone planet, because the co-orbital would also be in the habitable zone. And finally, we also wanted to look for additional planets in this system. So I led an open time proposal to observe the target with the state-of-the-art ESPRESSO instrument at Paranal Observatory in Chile, and we were granted around 80 hours of observations. In total, we obtained 113 individual spectra from November 2018 to January 2020. The quality of the spectra were absolutely outstanding and provided 1 meter per second photon noise in 15-minute exposures for this relatively faint star with V magnitude 14. So we extracted the radial velocities using a binary mask and the data reduction software of the pipeline of the instrument, and we obtained this time series here, where I am showing the previous HARPS measurements in red, published by Ment and Dittmann, together with our new observations obtained with ESPRESSO. It is remarkable how the scatter decreases in this ESPRESSO new data set. In the panel below, I am showing the time series for the full width Hubble maximum of the cross-correlation function of the spectra, which is an indicator of the activity of the parent star. Indeed, you can see that this activity is translated into the radial velocity. You can see similar patterns in the full width Hubble maximum and the radial velocity. So we used these values, this full width Hubble maximum of the cross-correlation function, as a proxy to model the radial velocities, including the activity information. So we could isolate the contribution of the planetary signals from the activity, as I am showing here in this panel, where I removed the modeled stellar activity. Additionally, we used the TESS data from sector number 3, where this target was observed, and 1 transit from planet B was detected, and 5 transits from planet C were catched. We performed a joint analysis of the light curve and radial velocity data in a Bayesian framework, and we could detect easily both planets. I want you to focus here in the top panels, which show the radial velocities, where the greenish colors represent the ESPRESSO data, and the red represent the HARPS data, so that you can appreciate the smaller scatter from the ESPRESSO instrument. If you also focus on the y-axis, you see that we are seeing this star wobbling around the center of mass of the system with a velocity of around 2 meters per second, which is wonderful because we can clearly detect these variations, demonstrating the excellent machinery that ESPRESSO is. With these results, we could update the location of these 2 planets in the mass radius diagram that I'm showing here. So with dashed lines, I am showing the location of these 2 planets before our measurements, and the new values for the mass and the radius are shown with solid error bars. You can see the improvement in the mass uncertainty, which is very remarkable here. Both planets now lie on top, exactly on top of the Earth-like composition, but having different scales, with the inner component being smaller and less massive, and the habitable zone planet being a truly super Earth. The precision in mass now reaches 9% for the inner planet and 7% for the habitable world. This high precision now allowed us to perform a detailed internal structure analysis of both planets. Interestingly, the habitable planet is compatible with an oceanic world, having a core mass fraction of 49%, with a mantle of 47% mass, and a liquid water layer of 4%. Including the uncertainties, this means that LHS 1140b could potentially have between 5 and 80 times the amount of water that we have on Earth, being a truly water world. The inner planet, on the contrary here, I'm showing here the Earth for comparison, but the inner planet, on the contrary, seems to be really scarce in water. And it is another example of a Mercury-like composition with most of its mass located in the core. Now, the potentially large amount of liquid water in planet B, in a planet in the habitable zone, makes us wonder about how this water is distributed along the planet. As demonstrated by Yang and collaborators in 2020 last year, for this particular planet, if it is tidally locked, meaning that it always faces, it always has the same phase presents the same phase to its host star, the planet could be in an eyeball-like state, with most of the planet covered by ice, by an ice layer, while having the day side phase molted and showing the liquid ocean. However, depending on the greenhouse gases in the atmosphere, this could easily turn into a snowball with the deep ocean covered by a layer of ice. So studying its atmospheric composition is also really important to understand the landscape in this planet. Interestingly, a month ago, a paper by Edwards and collaborators published a potential water vapor in the atmosphere of this planet through Hubble observations, which point to a potential hydrologic cycle in this super-Earth planet. The top panel here shows the data, so the data points from Hubble and the water model in blue and the no water model in red. In the bottom panel, the authors present the differences in the results when using our updated physical properties from our paper last year, and they represent a 2.5 sigma tentative detection of water vapor in the atmosphere of this planet. But we not only tested the two-planet scenario. By taking advantage of the exquisite data set we obtained, we tested 15 additional models, including different number of planets and orbital configurations. In this figure, I'm showing is the Bayesian evidence we have for each of these 15 models here. Each of these models represent, so here in yellow, it's the no planet model. In pink, you see the one planet model. In orange, two planet models, and in green, the three planet models with different orbital configurations, eccentric, one of the planets being eccentric, the other circular, etc., etc. All possible combinations with three planets. And we found that the largest evidence indeed corresponds to the two-planet model with the two known planets in circular orbits. However, another model with three planets also seemed to show a large evidence with the third new planet candidate located at 79 days orbital period, just beyond the habitable zone. Indeed, we did the exercise of analyzing the evolution of this Bayesian evidence for the three-planet model as we add more data. The result showed that the Bayesian evidence that is shown in this panel here, and it showed that the Bayesian evidence for the three-planet model steadily increases against the two-planet model as we add new measurements to the data set, as it's clearly shown in this figure. This is a clear sign that some signal is popping up at that periodicity. This additional signal is shown in this panel, and it would correspond to a 4.8 Earth masses planet. When checking the test light curve again against the ephemerides of the new planet candidate, because of course, if the planet is coplanar with the inner two confirmed planets, the planet would transit. So we checked the test light curves, and we found that unfortunately, the transit of the planet occurred right before the start of sector number 3. In pink, here I'm showing the posterior distribution of the times of the transits for this third planet candidate, and in gray the actual observations from tests. And you can see that in sector 3, the transit of the planet occurred right before the sector 3 observations, and even more unfortunate, the recently published observations from sector 13 lie exactly in between two transits of this planet. So as expected, we found no hints for the transit of this planet in the new test dataset, but this is consistent with the radial velocity ephemerides. Consequently, we could then not confirm the planet, but provide strong evidence for its existence. We are also carrying out additional efforts to detect this signal at the moment. Detecting the transit of this third planet is really important, as it lies exactly in the mass regime where the two populations at both sides of the radius valley diverge into volatile and gas-dominated worlds, represented by this shaded region here. So having a transit would allow us to have a point in the y-axis, and so place the planet in this mass radius diagram. So as a bonus track, and I'm finishing here, we looked for co-orbital worlds also in sharing the orbital path with the two confirmed planets, so the one in the habitable zone and the inner component. While we could discard this scenario for the habitable zone planet, so we could discard any co-orbital with a very low limit to the habitable zone planet, we found a positive hint in the radial velocity data pointing to a small sub-Earth mass orbit companion. So this means that the interior planet may shows an imbalance in the mass between the Lagrangian point L4 and L5, which could point to an actual Trojan planet. When checking the test light curve, which is shown in this panel, we indeed found a small dimming exact same location, same Lagrangian point as the radial velocity data pointed to the presence of the Trojan planet, which we don't see in the L5 Lagrangian point. This is very interesting, and we are also working on this potentially interesting scenario. So we revisited the LHS 1140 system with more than 100 ESPRESSO measurements and test data to provide the best density precision achieved for a rocky world. We provided detailed analysis on the internal structure of these planets using this information, and we concluded that the habitable zone planet might be a truly oceanic world, harboring at least 5 times more water than the Earth. And I would like to finish my talk with this portrait of the compact, the young, and the habitable, transiting multi-planetary systems that, to a large monitoring effort, are now one of the best systems to further characterize their atmospheric and internal structure properties. Something that Plato, on the other side, will do for many other systems in the coming years. And I will stop here and take any questions you may have.
Thank you, Jorge. Thank you very much. Thank you very much for this nice presentation. Many different planets. So while I wait for questions, so if you have any questions, you can also put them in the chat, and then I'll read them loud. And we can start with questions. I think Hector Vives Arias, he has one, so please unmute your microphone.
Hi, can you hear me?
Yes.
Well, I have 2 questions. So I'll start with the first one. In the compact system, you said it's an analog to a solar system. So I was wondering if all the planets are inside the snow line, or are some of them outside?
Good question. I think all of them are inside the snow line, so it's different in that sense.
Okay, so they should have migrated if they formed, the big ones formed because they were inside the snow line.
Mm-hmm. Indeed, yes.
Okay, and the second
migration here.
Okay, and the second question would be like if Mercury-like planets are common in extrasolar systems. I think, am I correct in assuming the explanation that was given with a giant impact to remove most of the mantle on Mercury is still correct, or?
Yeah, that's a very good question. First of all, we don't know if Mercury analogs are common. It happened that in these systems we found several of them actually, which is pretty interesting. But we don't know if they are common. But if they are common, yes, the great impact theory might still be a possibility to explain this large core fraction. So they lost all the mantle in this giant impact.
Okay, so the abundance of extrasolar Mercuries could it tip the balance between some hypotheses or others?
Between what, sorry?
Between hypotheses for the formation of Mercury and the large core it has?
I don't think we have a large enough population of Mercury analogs to say that so far. I don't think so.
Yeah, my question was like, with more statistics, could the abundance help distinguish between hypotheses, or is it?
I think it's a difficult. I think only population synthesis it will hint at the answer, but I don't think we'll have the definitive answer. We still need to understand if they really don't have an atmosphere, for instance, because our internal structure models indicate that they don't in these particular cases, but it would be great to try and observe the atmosphere, because if they have an atmosphere, it's very difficult that the giant impact scenario took place.
Okay, thank you. And that was a great talk. Thanks.
Thank you, Hector. So next is Adrian.
Hi, Jorge. Thanks so much for your nice talk. It was for me awesome. It's incredible the great the interesting results you can obtain about exoplanets with ESPRESSO and all these new observatories. I would like to make a question about the please, can you go back to the ternary diagrams you choose, the triangle diagram with the internal composition of the planet?
Mm-hmm. This one?
Yes.
Okay.
I found it really interesting because, you know, I'm not sure, but it reminds me the ternary diagram you use in thermodynamics or in general in physical chemistry when you have a ternary mixture of the different fractions. Then in this case, the composition is driven by the chemical potential or in temperature. My question is, how are you so sure that just estimating the position of the planet, the amount of radiation this planet can receive from the star, how can you be so sure about the internal structure without knowing, for instance, the chemical composition or even some I mean, in my views, it strongly relies on the models. Is it right or no?
Yeah, absolutely. Yes. Our models, so the techniques we are using rely not only on the mass and the radius of the planets that we can get, but also on the chemical composition of the cloud where the planet was formed. And this is obtained through the chemical study of the star itself. So depending on the abundances of the chemical elements in the star, this is the input for our internal structure methods to derive the internal composition. So yes, we are taking into account the chemical abundances, assuming that the planet was formed there, exactly there, and was not catched from anywhere else. So assuming that, we have the chemical composition of the cloud where it was formed, and we can infer.
How much do you know, or how much are you able to estimate the chemical composition? I mean, for instance, imagine you have small traces of the different elements. In that case, the internal composition should change dramatically because of perhaps for instance, I once read that the internal composition of Mercury can completely change even the movement or the possible tectonics of the planets.
Mm-hmm. Yeah, no, I mean, so I didn't include the uncertainties here, but for instance, we have a 10% uncertainty in the core mass fraction, and I think it's around 12% in the mantle. Mm-hmm. And for the water, it's even between 0.5% and 8%. So there's a lot of margin here. Mm-hmm. But the chemical composition of the star is very precisely known, because you have to think that we have more than 300 spectra of this star that we can stack together and analyze the stacked spectrum. So we have a lot of, a very high signal to noise spectrum with very high resolution. So if you go to the paper, there's a table with all the chemical abundances of the star, and you can check the precision of this in these chemical abundances, which is very, very good.
Can you say anything about tectonics, about the possibility of tectonic activity in these worlds?
We didn't do this analysis in the paper, but I think it was yesterday. There was a paper on exactly this on LHS. I think it's LHS 3844. Where they try to detect plate tectonics in these extrasolar planets, and I found the paper very interesting. I didn't go into the details, but this is starting to be done. In this case, we didn't.
Okay, thank you so much.
Thank you.
Thank you. So I guess what you were saying is that the chemical composition that you assume for the planets, so considers that the composition of the protosolar nebula was the same as the chemical composition of the central star.
Exactly, yes.
Okay. And then you consider a certain composition for the core always and for the mantle, and depending on the abundances of the elements,
exactly,
then you assign a fraction for the mantle and then another fraction for the core.
Having the abundance of the chemical abundances of the star allows you to break some degeneracies between the core and mantle.
Yeah. Okay.
The abundances, yes.
Okay. And an uncertainty of 10%, I think, is a bit.
Sorry?
Small. I think an uncertainty of 10% is a bit small still for this.
Yeah, that's 1 sigma. So you have to think this as 1 sigma. I don't think it's 10%. So if the whole range of possibilities is much larger than 10%. Yes.
Right.
But in this case in particular, we have a lot of very good chemical abundances. So I think it's quite reliable.
All right.
But still 1 sigma.
Yes. Yeah. Okay. So we have 2 other questions. Well, Laura's question was answered because it was the same as this one. And then Teresa Martinez has another question. And then she asks, I didn't get, how did you choose the habitable zone?
Okay.
So maybe you can explain.
Let's go maybe to this figure here. Yeah, so the habitable zone is the region around the star where so we define the habitable zone as the region around the star where the planet is not so close that water can evaporate, and it's not too far away so that the potential water in the surface of the planet could be frozen. So in this region, the irradiation of the star allows water in the surface of the planet to be in liquid state. That's how habitable zone is defined. And in this case, it's between 15 and 45 days, something like that.
Mm-hmm. Thank you. Mm-hmm. And I think I have a question related also to the how to infer the interior structure of these planets. And I don't know whether you're aware, but there are studies that have been done in radio with radio wavelengths. And in principle, so these people, they are trying to detect the auroral emission in systems with planets. And I think there's a paper recently that has come out recently with the system, the Proxima B,
Yes, yes.
where apparently they have detected this kind of bursting emission that seems to be associated with this kind of phenomenon. And that would imply that the planet has a magnetosphere. And then you can infer the information about the structure, the physical structure of the interior. So that would be a nice thing to do. You know, now that you have all these different types of systems, of multi-planetary systems, it would be nice to check that you can see these kind of effects.
Yeah, digging into the magnetic field. Yeah, that's a whole new world.
Yeah, yeah. This is something that the SKA will try to do.
Yeah, yeah.
In the future.
Indeed. Yes. Yeah,
Okay.
good candidates.
Yeah. Okay. So, are there any other questions?